Next example, let v is equal to r square and u is xy, v is x dash y dash, alpha is in scalar, alpha belongs to r. We define addition and scalar multiplication as follows: u plus v is equal to, that is addition of this xy plus x dash y dash is what? X plus x dash plus 1 and y plus y dash plus 1. So addition of these two. And alpha x into y, xy, alpha into xy is alpha x alpha y. That is the scalar multiplication, is usual scalar multiplication, but the addition of two vectors is not the usual addition. What is the usual addition of this u and v? Is order pair x plus x dash comma y plus y dash. This is not x plus x dash. It is x dash x plus x dash plus 1, y plus y dash plus 1. So we have to verify is v vector space. So when v is a vector space, if v satisfies the 10 properties, and when v is not vector space, if out of the 10 properties any one property fails for this set with respect to these two operations, and here the operation scalar multiplication is usual scalar multiplication, means the properties are corresponding to related to scalar multiplication are satisfied for this set. What are that properties? Property number C2 and M1, M2, M3, M4. So we have to concentrate on the property of additions corresponds to related to addition. That is the property number C1 and A1, A2, A3, A4. So out of these 5 property, one of the property, at least one of the property may fails for this set with respect to this addition operation addition. So we have to concentrate that on that property, and we have to write the solution that if V is not vector space, then out of these 5 property, one of the property fails for this set. So we have to write the counter example for that property, and that this is the answer. Don't write this answer, that is the property holds for the set. This answer is not essential. We have to write only that property which dissatisfied for the set, and this is the property. What is the property? That alpha u plus v is not equal to alpha u plus alpha v. So in another notation, we have to show the k u plus v, k u bar plus v bar is not equal to k u bar plus k u bar. That is the M1 property. Either use notation for scalars as alpha beta or small k small l. Okay, and vectors, that is the elements of vector space, are denoted by u bar, v bar, or just ub. So we have to show this property M1 fails. What is the property? That is the k u plus v is equal to k u plus kv. So this is the property. Okay, when we have to show this property fails for the set, that is where to give the counter example. Either write this proof. What is this? This is the general proof, general statement. That is general elements. Take u bar as x, y, z, v bar as x dash, y dash, z dash. And then what is the LHS? Alpha, the value of alpha in bracket u bar plus v bar is this alpha, x plus x dash plus 1, y plus y dash plus 1. This is by using the definition. U bar plus v bar or u plus v is by using this definition. This is the definition: x plus x dash plus 1, y plus y dash plus 1. Because addition is not usual addition. And then alpha into this is what? Alpha to multiply to this first component, comma alpha into. And this is again by using this definition. Alpha x y is alpha x alpha y. And therefore we have, after multiplying this alpha and with the bracket, we have this. So this is the LHS, alpha u bar plus v bar, or alpha u plus v. And now what is RHS? Alpha u plus alpha v. So alpha u is what? Alpha u is alpha x alpha y, alpha x alpha y. Okay. And what is alpha v is alpha x dash alpha y dash. And what is their addition? Alpha x plus alpha x dash plus 1, alpha y plus alpha y dash plus 1. So write first alpha u plus alpha v. So alpha u plus alpha, we write alpha u is alpha x alpha y, and alpha v is alpha x dash alpha y dash, and their addition is this. by using this definition. Multiplication, scalar multiplication, this definition, addition is this definition. And what is your observation? This is alpha u plus v, and this is alpha u plus alpha v. So these two are not equal. These two are not equal. We have alpha u plus v is this, and alpha u plus alpha v is this. These two are not equal. So, and therefore we say M1 fails, and therefore V is not vector space under these two operations. So we can also give the answer of this problem by using counter example, by taking counter example, by giving the counter example. So what is the, take alpha is as a particular scalar, suppose 2. Instead of 2, we can also take 3, 4, minus 2, minus 5. Then u bar as 2, 3, or we take another element, and v bar as 4, minus 1. So these are not fixed element. We can also take u bar and v bar another values of the element of R2, any two elements. Then what is u plus v? 2, 3 plus 4 minus 1 is 2 plus 4 plus 1 by using this definition. Addition is by using this definition. What is the addition of x, y and x dash, y dash? X plus x dash plus 1, y plus y dash plus 1. So addition of 2, 3 plus 4 minus 1 is 2 plus 4 plus 1, and 3 minus 1 plus 1. That is 7, 3. And what is alpha into, in bracket, u bar plus v bar is 2, 7, 3 is 14, 6, because by using this definition, alpha u x y is alpha x, alpha y. So 2, 7, 3 is 14, 6. So this is the LHS. Now find alpha u bar. Alpha u bar is what? 2. Alpha is 2. U bar is 2, 3. And it is 4, 6. Alpha v bar is 2. 4 minus 1 is 8 minus 2. And what is alpha u bar plus alpha v bar? Is 4, 6 plus 8 minus 2 is 4 plus 8 plus 1, comma 6 plus 6 minus 2 plus 1 by using the definition given in the problem. And it is 13, 5. So this is alpha u bar plus v bar is 14, 6. And this is 15, 5, 13, 5. Alpha u bar plus v bar. So alpha u bar plus v bar means this is not equal to alpha u bar plus alpha v bar. And therefore property M1 fails, and therefore V is equal to R2 is not vector space under these two operations. So either give the this answer. I think this particular, by using by taking alpha u bar v bar particular elements of R2 and scalar alpha, we can give the answer. So this is called counter example. So in order to show the vector space is not set is not vector space, give the counter example. Okay, and that is the AG answer. That is out of the 10 property. M2 also fails for this set, but no need to write M2 fails. Just write any one counter example for any one property. So next is, let A is V is equal to the set of 2 by 2 matrices of this type A1, 1B. So these entries are fixed. So AB are real number. So obviously this is the subset. This V is subset of set of all 2 by 2 matrices, that is M2 by 2R. So is not vector space with respect to usual addition and usual scalar multiplication, as C1 and C2 fails. C1 and C2 fails. So out of these two properties, give any one example. So if you take two elements from V as suppose 2, 1, 1, 3, and another element of V as 4, 1, 1, 5, and if you take the addition of these two vectors, these two elements of V, then it is not the element of V. The addition of the two element is not element of V, because these entries are not equal to 1. Then now we have 2 at this place, and so this is not close for addition. V is not close for addition. Addition of any two elements of V does not belongs to V. Addition of some element of V does not belongs to V. So give the counter example and show C1 fails. Also we can show C2 also fails. So if we take this element as a 2, 1, 1, 3, and if we take a scalar as 2, then 2 into this element becomes, here we have 2, here we have 2, and it is not the element. C2 fails also. So give any one counter example for either C1 or C2 and show this set is not vector space. So let V is equal to A is this is the set of again 2 by 2 matrices A plus B, A plus B, B. So this is a vector space with respect to usual addition and scalar multiplication. This is the vector space. So we have to prove this answer of this problem is what? We have to write the 10 properties, that all the 10 properties satisfied for this set. So this is again the set of 2 by 2 matrices, and this set is what? Is a vector space. So next example, let V is equal to 1x set of order pair such that x belongs to R. So what are the elements of this set? This is the subset of R square. This V is the subset of R square. And what are the elements? 1 4, 1 5, 1 minus 1, 1 0, 1 9. These are the element of this set A, V. So this is the subset of R2. And for U is equal to 1x and V is equal to 1y, definition of addition is this: U plus V is 1, 1, 1 plus 1 is not 1, 2, it is 1, x plus y. And alpha into U is what? 1 alpha x. And this is, then V is a vector space. So that V is a vector space with respect to these two operations. Okay, that is why I have to write the all 10 properties, all the 10 proof of all the 10 properties. So this is the vector space. So this is the proof. So addition of every two element belongs to U. This holds C1, C2, A1, A2 holds. This is the proof of A3, A4. So what is the zero element? 1 0 is the zero vector, because if you add 1 0, then we have the answer 1 0. Same, that is the 1 0 is the zero of this set, because if you add 1 0, then we have the answer 1 0. And the negative of each element, 1 minus x. If V is the element, U is the element 1x, then its negative is 1 minus x. So it belongs to. So this is the proof of M1, M2, M3, M4. All the properties are satisfied for this set, 10 properties, and therefore this set V is a vector space. So next example, V is equal to R2, and for U is equal to xy and V is equal to x dash y that belongs to R square. Alpha is belongs to R, means scalar. Definition of this U plus V is x into x dash comma y into y dash, and alpha U is what? Alpha x, alpha y. So show that V is equal to R square is not a vector space, real vector space, or is not vector space under these two operations. So if we observe the operation scalar multiplication, it is a usual scalar multiplication, but the addition is not usual addition. So what is the usual addition of this xy plus x dash y dash? Is x plus x dash comma y plus y dash, but it is not x plus x dash, it is x into x dash, y into y dash. So I have to concentrate on the properties corresponds to addition, 5 properties. So out of that, this property M1 fails. What is M1? Alpha U plus V is not equal to alpha U plus alpha V. So by taking counter example, we can show that this is not satisfied. That is like this answer, give the answer. That is, take alpha as 2, U bar as 2 3, V bar as 4 minus 1, and then find the LHS and RHS, okay, separately. Find the value of alpha U bar plus V bar separately, alpha U bar plus alpha V bar separately, okay. And while taking the addition, use this definition. So give the counter example, or this proof is also we can give this proof. M1 fails, also M2 fails, okay. So give the counter example or write this proof. Write any one condition. M2 also fails. So this V is not vector space. Give the counter example. Take alpha as a element number, suppose 2, then U bar and V bar as a particular element, and show, find alpha plus beta U bar and alpha U bar plus V bar and alpha U bar alpha V bar separately, and show these two are not equal. Let V is equal to set of matrices of 2 by 2 order matrices such that A inverse exists, or determinant of A is not equal to 0. So this is again the subset of this is subset of M2 by 2R. So take the elements whose inverses exist in M2 by 2R. Is not a vector space with respect to usual addition and usual scalar multiplication, as the property C1, A1, A3, A4 fails. Okay. How can show C1 fails? Because the addition of two matrix, invertible matrix, is not necessarily invertible matrix. That is, if we take the two elements of V, then its addition not necessarily invertible matrix. Okay. Also we can show a1 a through. So write the counter example for this property. Out of this four property, write in write a counter example. That is the uh, take two elements from V such that their inverse exist, but that is the determinant of that two matrix is not equal to 0. But their addition, after taking addition, we have the two matrix of order 2 by 2, and its determinant is 0. So we have to write the counter example for C1 or A1 or A3 or A4. Let V be this set A1 1B, AB belongs to R, and then again V is what? Set of 2 by 2 matrices. For A1 is equal to this, B1 is equal to this, addition is this, and scalar multiplication is this. Then show that V is a vector space. Under these two operations, this set is a vector space. Means we have to write the 10 properties, proof of 10 properties. And this V is R2, and the for addition is defined like this. This is usual addition, but scalar multiplication is what? Alpha is 0. So M4 property fails. 1 into U bar is not equal to U bar, because 1 into U bar is 1. Suppose U bar is 1, 2, 3, 4, and then you could take 1 into U bar by using this, then it is not 2, 4, it is 2, 0. 2, 0. Okay, and it is not equal to 1 into U bar is not equal to U bar, and therefore V is equal to R2 is not a real vector space, or is not vector space with respect to these two operations. This is called weak vector space. This is called weak vector space. So the next problem is show that R square, okay, V is this set, Y is equal to mx, equation of straight line, Y is equal to mx, and then this is a vector space. Okay, so exercise problem, we have to solve all these problems. For those that are not, list all the axioms that fails to hold. Okay, so determine these are the vector spaces or not vector spaces. So think on these exercise. So these are the operations. Obviously this is the not usual scalar multiplication, and we know that this is not vector space. R3 is not vector space under these two operations. So write answer of all these problems. If you observe this problem, then it is again the scalar multiplication is not usual scalar multiplication, and so it may not be, this R3 is not vector space under these two operations, maybe. So think all about these examples and give the counter example. If the vector space, if the set is not vector space, give the counter example. So these are also the some exercise examples. So we will discuss all these examples in the next lecture.